tomorrow, the school is not here. It's at the Principia Institute, right by the hotel, right? So, at 9:30. Okay, so we start the next round of talks. We move a little bit away from brain dynamics, and Guilherme is going to talk about some work we did together. Please.
Okay, can you hear me well? Okay, so as Professor Marcos says, I'm Guilherme. I am a postdoc here at the ICTP, and today I will present some of my works with my collaborators, Professor Marcel Novaes and Professor Marcos Aguiar, entitled Bifurcations in the Kuramoto Model with the External Forcing and Higher Order Interactions. And I will make use of the past lectures of this week, and I hope that you are convinced the utility and the importance of the Kuramoto model in trying to investigate and understand synchronization phenomena. And since the model was proposed in the 70s, a lot of extensions were proposed as well, such as matrix coupling, frustration, and other stuff. And one of these extensions that is really important is the coupling with external forcing. And when we say external forcing, we're saying that I have an external an exterior of the oscillators, and I even try to understand how these oscillators will synchronize with this external drive, or they will maintain their whole dynamic. And do not see these external forces. And this kind of phenomena is important is found in nature and is important in such phenomena such as circadian rhythms, artificial pacemakers, and epileptic seizures, in which we have some external stimuli to the oscillators, and then they will change their dynamic according to this. And we also add another ingredient in this kind of systems, because in many complex systems, the interactions, they go beyond pairwise. So we have a lot of elements, and their interactions are in triplets or in tetrahedra, and these interactions cannot be decomposed in pairwise. And we try to investigate what happened when we put this kind of interactions in the Kuramoto model. So when combining these two features, we add simultaneously the external forces and these higher order interactions, construct the equations, and characterize their dynamics in order to understand what kind of phenomena will arise from this. Okay, so first we have the Kuramoto equation. I believe you are more familiarized with these two first terms. We have a population of oscillators described by a single phase theta, and each one of these oscillators have a natural frequency, omega, that was drawn from a given distribution, for example, a Gaussian or a Lorentzian. And the coupling between each pair of oscillator is on this kind, in which K1 is the intensity of these interactions. And we add two new terms regarding three-body interactions and four-body interactions. And what it's important here is that the functional form of these interactions is not unique. So there are several ways to write the interactions between three oscillators in the Kuramoto model, but we choose these two for some reasons. The first one is that since the coefficient of the focal node theta I is the same in all equations, it's one of the equations that can be treated analytically. So you can, for example, put another coefficient here and rewrite the equation in another way, but you lose the capacity of applying the more traditional methods to investigate this analytically. Okay, so each one of these terms represent the three-bar interaction, and the intensity is K2, because a three-bar interaction is a two simplex, and in the four-bar interaction will be mediated by a coupling K3, because it's a three simplex. Okay? And we also have the external force with intensity F and frequency sigma. Okay? In the same way as all the works with Kuramoto, we will characterize the degree of synchronicity of this system by the Kuramoto order parameter, Z, which is represented by a modulus and a phase, and is basically the sum of the phases of each oscillator individually. But here we have a dynamic equation for each oscillator. So we have a high-dimensional system, and under certain conditions, we can use the autoantons and ansatz and try to reduce the number of equations and write from the dynamic equations of the individual modules equations for the dynamical of the order parameter. So we can write under some conditions that I will not detail here, dynamic equations for the module of Z and the phase of Z. And this equation is extremely more simple to analyze and calculate the bifurcation diagrams. And what draws our attention here is that the coupling of the 3 and 4 body terms, K2 and K3, they add up. So we can consider this as a single parameter in our model. And we also changed to a frame of reference that rotates with the external drive to get rid of the explicit time dependence of the equations. So the frequency that the system rotates is a combination between the natural frequency of the system and the frequency of the external drive. Okay? So here we can impose the conditions for calculating the saddle node and the hop bifurcations and find those manifolds. And for more complex bifurcations, we can use computational frameworks. And we have a typical bifurcation diagram in the F omega space. So we're fixing the coupling between the modules, K1 equals 1, and K2, 3 equals 7, which we will refer as simplicial parameters, and vary the force and the frequency, and calculate all these manifolds. I don't know if the quality is good, but we have a legend here to try to understand all these curves. We have full lines are the saddle node ones. We have a upper saddle node in black, and a lower saddle node here in green. The dotted line are snipers, which are saddle nodes with infinite period. These dotted lines here in black and here in green. We have also the dashed line, which are the hop, each one emanating from one saddle node manifold. We have one hop here in blue and one hop here in red. And the dot dashed is the homoclinic in pink that appears only on this zoom of the regions here. So these lines, they cross, they intersect, and they divide the region, this plane, in several regions, each one with their own fixed points and orbits. We named each one of them as a capital letter, and by zooming in, for example, in this region, we can see that we have two new behaviors here, the region F and region A. If we zoom in the tip of the region C, we can see the homoclinic that connects the Takens-Bogdanov point with the initial of the sniper bifurcation and define some very narrow regions, but also important. And if we zoom in the tip of the upper saddle node, we can also see those small regions here. But this diagram does not offer us a lot of information of what's going on in each one of the regions. So we can plot, for example, some string plots and all the equilibrium solutions of each one of these regions, region A, B, C, and so on. I will not enter into detail in all of them, but you can see that in some regions we have a stability between mutual synchronization and the forced synchronization. For example, like this, fixed point will represent synchronization with the external forces, and the periodic orbits are synchronization within the oscillators, the mutual entrainment. So here we have a stability between those two solutions. Then from A to B, the system undergoes a hop bifurcation, and we have just one solution again. And then we can see in region E a stability between two synchronized solutions with the external forces, and so on. Have a very rich and complex behavior here. We can also vary some parameters. For example, we keep them as fixed in each one of the panels, but vary them within the panels to see what happened with those manifolds. You can see if K1 is 1 and K2 is 5.8, there is not a double manifold, a double saddle node manifold, and the two hops, they emerge from the single, from just one saddle node, and this creates another region that was not, that do not appear on the previous figure, And if we keep increasing the K2 tree in these sequences, we see that this second manifold arises, and then they stretches and dominates the whole dynamic for the system. But if we fix K2 tree and vary K1, we can see that this manifold also stretches, but as K1 is larger than 2, the green manifold disappears, and we recover the bifurcation diagram for the model without the higher order interactions. Okay, we can also think about fixing the forcing parameters and vary the coupling, but in a certain way that we are projecting our 4-dimensional parameter space into these two projectors, but we found the same regions, but in a different shape. Okay, so concluding remarks, we extended the bifurcation analysis of the forced Kuramoto model to include these higher order interactions and also the forcing parameters. We could characterize the system both in the F omega plane and K1, K2 planes. And these two branches of the saddle node and the hop, they appear for a certain range of parameters, a large interval of those parameters. And the combined effect of those ingredients leads to a very rich and complex diagram divided into 11 different topological regions. That's what I have to talk. Thank you.
Okay, thank you, Guilherme. Questions or comments?
Thank you very much, Guilherme. What do you think is the most striking difference with respect to the case with and without the higher order interactions?
Okay, the first case is that without the higher order interactions, we do not have bistability in any cases. So when we put the higher order term, these manifold, they doubled, so this manifold doubles, that represents the bistability in the higher order. So the higher order adds this kind of behavior that was not found just in the pairwise interaction. So,
Thank you. I have seen that you have considered only like a couple of corrections, I think. It was 1 or 2 corrections in the higher order interactions.
Yeah.
What if you go higher? What do you
expect?
expect?
We have a recent paper that we were writing that in which we consider general order. So, but we do not investigated what happened when you put these general orders and the forcing. But we have we found a new behavior on this diagram here, because when you don't have the force, this is the phase diagram of the system in which this saddle node stretches from this instead of going with the hop the hop bifurcation, it stretches up. So you add another region that represents bistability between two highly synchronized solutions, because the bistability in this case is between an unsynchronized and a synchronized one. When you add 5, 6, and so on, you have this new region between the bistability between two highly synchronized regions.
It's following Pablo's question. So you say that with this high order interaction, you have bistability, but there is a minimum value, a threshold to get it, or it's a singular perturbation?
Okay, the bistability arises when k is smaller than 2.
K1 smaller than 2. Yeah.
So that's the only region in which you can have bistability. That's why this graph here, E, in which K1 is equals 2.1, does not have the bistability.
Okay, so thank you, Guilherme. So next speaker would be Fernando, but he